You were there just
Doesn't seem to
a
want to
minute
let
ago,
me.
though.
Oh, there, I got it. I found the button. Okay, great.
Okay,
Hi, everybody.
perfect. Okay,
Okay.
hi everyone. Um, Thanks for joining. So I just started a recording, so people who were just joining us, anyway, we were having some technical problems. I think we found a solution. Thanks, JJ, for improvising at the end. We did some tests, but it worked well during the test. Obviously, that's how it works all the time. So anyway, before I let JJ take control of his talk and the presentation, I just want to say a quick word. Welcome to our webinar. First of all, my name is Julie. So I run the program called Discover the Universe, and our goal is really to help teachers and educators, anyone who works with groups, youth groups, actually. If you want to learn more about astronomy, we're there to help you. So we have webinars throughout the year on different subjects, and I'm very happy today that we have a guest speaker joining us from Victoria. JJ Kavelaars is an expert on small bodies in the solar system. Actually, when I worked in Victoria, that was over 15 years ago, I love getting in touch with JJ because we always had cool stuff. Like at some point, I was giving a talk on Jupiter, and in the meantime, anyway, between 2 weeks, JJ had discovered new moons around Jupiter, which I thought was fascinating. So anyway, I like to keep up with what he does, and I'm glad he accepted to give this talk today about the edge of our solar system, and mostly the flyby of the object called Ultima Thule. So anyway, he'll tell you all about that. If you have questions, I'm not sure JJ will see them as we go along because he's sharing his screen right now, but we'll come back to them at the end. So, or maybe if there's something really relevant, JJ, if you don't mind, maybe I might turn on my microphone just to
Yeah.
ask it with audio instead, if it's really relevant to one specific question. But slide. But please, you can type questions, and if not, he'll take them at the end. So thanks a lot,
Great.
everyone, for being
Thanks,
there.
Julie.
And
I'm really glad to be here. This is very exciting to participate and discover the universe. And please do, if you have a question and you type it in the chat, Julie, if you could read it out, because I've closed the little chat box so that it doesn't take up space on the screen. So, but I would love to hear your questions as we go along, because it really helps to build the kind of interactivity that is really valuable in these presentations. So, I'm going to give you my presentation here, which is exploring a new world at the edge of the solar system. And that new world is now given the what we call informal name Ultima Thule, and its official designation from the Minor Planet Center is 2014 MU69. Most of the time I will just call it MU69. So that's my my standard kind of way of describing that object. So, okay, so this adventure that I want to take you on starts here. So this is one of the videos that I wanted to show, and hopefully you can hear a bit of the audio.
And liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. For 15 seconds, everything continues to look good as the atmospheric vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
Bye-bye, New Horizons. So, what an amazing launch. If you ever have a chance to be in near a launch site at a launch time, I go and see the launch. They're pretty amazing. The video doesn't quite capture the astonishingly fast ascent of the rocket. I mean, it's like, wow, it just went up into space. It's gone. That was a 30-second or 38-second clip, and you see the entire launch is over. It's a bit of a, you make a trip down to Florida to watch one of these launches, if that's what I've done anyway, and the whole trip is over in 40 seconds because that's the end of the launch, but it's still pretty impressive to watch. So that was New Horizons going out into space. That was the fastest launch of a civilian spacecraft ever, and still is. That was launched from the Earth at around 24 kilometers per second from the Earth. The orbit speed of the Earth around the Sun is 29 kilometers per second. So it was just a little bit slower than the entire gravitational pull of the Sun at our current distance from the Sun. So an enormously powerful launch coming off of the planet. Now that was done because the idea was that we wanted to get that spacecraft out to Pluto as fast as we could, because Pluto had already passed its closest approach point to the sun, its perihelion. It had passed that already a few years back, a decade earlier, really, and we were just anxious that we needed to get out there and see what Pluto was like before it got any farther from the sun and got any colder. There was a real hope that some interesting atmospherics would be going on Pluto as it warmed up. So I just want to start the story with that idea that that's what's going on. We are launching this thing at super high speed out into the solar system. So this is what was on board that rocket. This is the New Horizons spacecraft, the entire payload shown there. We have on board these 7 instruments, although some of them are actually doubled up. So LORRI is the main instrument that you see a lot of the press images from. It's the long-range reconnaissance imager. It takes the high-resolution but white light images of things that the spacecraft is flying past. And then we have, sticking out the back of that thing, you can see this black thing that's not labeled. That's the radioactive power generator. There's a big chunk of plutonium back there, and it's decaying away and producing heat, and there's a thermocoupler that's turning that heat into electricity. And so the entire spacecraft is powered off that bit of plutonium that's decaying away, but running the entire spacecraft while it goes. You can also see, so you see here's LORRI down here. You can see the input here to this thing called RALPH, and RALPH is the color imager. It takes color and infrared images of the thing that is pointed at. And you can see that RALPH and LORRI are kind of pointing basically in the same direction. And then we have here ALICE, which is another camera, which is going to be doing ultraviolet spectroscopy. And then we have another sort of input here, which is pointing off to the side, which is not part of the science experiment. Sticking underneath the spacecraft, which you can't see, is a thing called the student dust counter. This was built by university students and attached to the spacecraft and runs an entirely separate experiment that's counting the amount of dust in our solar system. And then the solar wind and particle experiments over here, which were more about the environment the spacecraft's flying through. And this is actually the communications antenna, and also the an experiment for measuring radio temperature. So you can point this at an object and measure its temperature by measuring its radio emission. The thing to look at here is to notice that the RALPH imager here and the LORRI imager, they point off in this direction to look at the objects. You have to point the spacecraft kind of along that axis to see what's going on. And then we turn the spacecraft and we point the antenna at the Earth to transmit data back. And so there are 2 different orientations the spacecraft has, and we have to choose between observing something and downlinking data. And we flip-flop back and forth between them. And all of the actions of the spacecraft are done by thrusters. There are small heterozyne thrusters on board. There are 6 of them, and they steer the spacecraft around so you can point at different things. So that is the New Horizons in a very quick nutshell. And here is what its first mission was, this beautiful flight through the Pluto system. So we went past Pluto, we saw this beautiful glacier, this giant nitrogen glacier on the surface of Pluto, this mysterious red material over here. We have this region of Charon here, and this kind of unusual red stuff on top of here. This red material over here on Pluto is going to turn out to be very important in understanding MU69. Pluto also has a bunch of small little satellites, and these were kind of like hints about what it was we might be seeing when we got to MU69. We're really expecting that the target is going to end up looking maybe a little bit like one of these things, but we're going to get closer to it and have higher resolution imaging. So that's kind of setting the stage. And since Pluto is so beautiful, I'm going to give you one video here of flying over Pluto's terrain. So this is just taking all the data from the encounter and stitching it together on a sort of spherical projection and giving you a sense of being the spacecraft and flying over and looking down at the surface of Pluto as you're flying past. And that really captures some of the drama of this whole thing. And you can see here these mountains here rising up out of the ice glacier, the nitrogen glacier, and these are ice mountains floating on top of the nitrogen. And it's just a beautiful, beautiful thing to look at, the whole encounter. I mean, I could just stare at this video all day, really. There's these pockmarked, these craters on here, which are good to keep your mind on, that there are these beautiful craters on Pluto's surface. And what we noticed immediately was this nitrogen glacier has almost no craters. In fact, it has no craters on it. And so it's a very young feature, which means there's active ice flows happening on the surface of Pluto. So that is Pluto's beautiful terrain diversity shown in this lovely video. Okay, we are getting ready for that Pluto flyby, but at the same time, the science community is trying to understand what else they will do with the spacecraft after it's past Pluto. And so that was where trying to explore and understand the Kuiper Belt comes in. So here we have a map of what is the Kuiper Belt. This is a region of the outer solar system out beyond the orbit of Neptune that contains a lot of small bodies, some things maybe 1,000 kilometers in size-ish, like Pluto, up to or down to things that are, we knew at the time, hundreds of kilometers in size. And this is a plot of all the objects we knew of in 1999, on January 28th, 1999. I just happened to make this plot at that time. And the point is that is basically what we understood about the outer solar system, the distribution of Kuiper Belt objects at the time that New Horizons was being built, right? 7 years before launch, you've locked in all the choices you're going to make about the camera systems and how the mission's going to go. These are all set at this point, and you're making those choices based on this distribution of material. You can see that we're going to go to Pluto, which is out here. And what the mission planning team said was, you know what, we're going to go past Pluto, and we know we've only just begun to explore the Kuiper Belt. So these little dots out here, this is an overview, this is a view from overhead of the solar system. So here's Jupiter and Saturn in their orbits, and here's Uranus and Neptune. We're going to get to Pluto, we're going to fly past it, and we're going to find something else to visit out here. And that's going to be easy to do, and we're going to have no problems, so we're going to do it. Yay. Okay. So what happens really, though, is that it turns out to be really hard. And we spent basically from the 1990s into the 2000s and then into the early 2000s, all the way up till about 2011, 2013 even, unsuccessfully trying to find something for the spacecraft to go past. I'm showing here what we understood about the Kuiper Belt in 2011. And this is from a paper that was published by a group that I work with called the Canada-France Ecliptic Plane Survey. We use one of Canada's telescopes in Hawaii, the Canada-France-Hawaii telescope, to survey the outer solar system and try to find as many Kuiper Belt objects as we could and get for ourselves a picture of what does the outer solar system, the Kuiper Belt, really look like. And this is going to be critical information for something like New Horizons to be able to find its way to another object out there. So this plot here, there's a dot on this plot for every object that the CFEPS group thought existed in the Kuiper Belt that was larger than 100 kilometers in diameter. So we made this model of the Kuiper Belt based on 183 detections. We had this 183 detections of objects in the Kuiper Belt, and we extrapolated that to these 100,000 points you see over here in this diagram to get an idea of what the actual structure was like. The CFEPS model, the CFEPS observations of the Kuiper Belt were really revealing for the first time some of the real detailed structure of the orbital distribution. And that detailed structure was revealing a couple of things that were slightly unexpected for the New Horizons mission. One of which was that the density of material really was right here in this little ring at almost exactly 43 astronomical units from the sun. So 1 astronomical unit is the Earth-Sun distance. You go 43 astronomical units out and you get this ring of material that we call the kernel. And that is just like the really core piece of the Kuiper Belt. And what we found was that basically for New Horizons, they would have to find an object in this kernel because the rest of the Kuiper Belt is just too low in density for a target to be found. The spacecraft only has a very limited amount of fuel and can only turn by about half a degree, which basically means, it could turn by the length, the angle that your finger occupies. If you hold your finger out at arm's length and you see your fingernail, you will have this sort of the amount of turning angle that was available, which is really tiny. So to find something along that cone that the spacecraft could get to would mean looking in the densest part of the Kuiper Belt, which turned out to be the kernel. And interestingly, the kernel isn't quite in the ecliptic plane. It's a little tilted up from the ecliptic plane. And so for the longest time, the search teams had been looking kind of in a much broader area of the solar system and looking kind of a little bit off where the highest density component of the Kuiper Belt was. So we brought to them this model and said, look, this is what the orbital distribution really looks like. This is where you really need to look to find your target. And so that's what they did. They refocused their searches on this exact area. So when they did that, we gave them this model basically of what the Kuiper Belt looks like. So over here we have this model of the Kuiper Belt showing there's a little dot here. This is like an image of the sky, sort of a diagram of what the sky would look like. Each one of these squares is a Hubble observing field. There are 83 fields that we're going to observe with Hubble, and each one of the red dots is a model of how many things the CFEPS, or is a representation of how many things CFEPS model thinks there will be that the spacecraft can get to. Only there's 100 times more dots in the image than there are actual objects to get to. So if you look at this, you can see there's a slight concentration towards the center of the field of these red dots. And really, you really have to look at just this exact center location according to this model. And the real thing was that we were showing them that you had to go very faint, you had to go exactly at this spot, and then there was a small chance you would actually see something. And to do all of that together in this part of the solar system where the star density is so high was going to require using Hubble. And so they were allocated, the team was allocated 166 orbits on the Hubble Space Telescope, which is a very large allocation to search for something for the spacecraft to get to. Here's a Hubble image. This is a Hubble image with a bunch of stars in it. That's what the field looks like. But then using software that removes the stars based on them being always in the same place, this is what an image will look like once you remove the stars. And so you can see that there's nothing there except a bit of noise around the brightest sources. And so that's what we said. We said, well, we could maybe find, maybe this thing right here is a Kuiper Belt object that we can find. So we'll try and do that. So we proposed to do this, and here's what we came up with. You have this image here of the six images in a series here of a part of the star field, and there's a little green circle to guide your eye where you can see this little thing moving along, and that was found in the very first Hubble field we took out of the 83 we were looking at exactly the center of the sweet spot where we thought we could find a target to encounter. And then up above you, we see a stacking of those images where the stars have been removed, like I showed in that previous image. So Hubble came to the rescue and managed to find for us this target right exactly where it was supposed to be. And this is, in the end, we found 3 targets in the end, which was right on the prediction of how many we thought the program would find. But we picked the first one we found because it was the one that really, it had a very low velocity requirement to get to. It was in the right spot, and that was where we wanted to go. So, okay, so that was MU69, and this is a slide from a presentation that we made on July 2014, where we said, this is the world we're going to go to. And I want you to look at that world. That was kind of our simulated concept of what we're looking for. There's a giant impact crater here at the top. There are lots of little small craters over a whole range of sizes present. It has some kind of oblongness to it. It's bright on one side. So that was our vision of what it was we were going to be seeing. So that vision is, of course, what you do is you try to understand how you had that vision and then what did you actually see and how different were they. So, okay, so at about the same time then, that was July 2014. So a year later, we had an orbit for this thing mapped out, and we had the Pluto encounter, and we had those beautiful images you saw at the start in the video, and then we turned the spacecraft back towards Pluto, and we saw Pluto in its silhouette with the sun being blocked by Pluto, this beautiful look at the atmosphere of Pluto, and that was our goodbye image of Pluto, essentially. Really a beautiful end to a so successful mission flying past Pluto. And now it's time to turn the spacecraft and point towards our real destination, which is going to be the Kuiper Belt. And let's go out and find 2014 MU69 and let's look at it. So that was done by proposing to NASA to extend the mission, and we were very fortunate that NASA funded this extension to this mission to keep operating this perfectly healthy spacecraft. What you can see in this image, though, is that by the time we got to making the proposal to NASA, we decided that maybe this would be a more realistic view of what that object looked like. Two things maybe stuck together in some kind of contact system with some unusual shading and maybe not so many craters. And this was like our evolving view of what the object that we're going to see is going to look like. And really, I'm trying to emphasize for you here that our understanding of the Kuiper Belt was just changing constantly, basically, as this mission is progressing. So, okay, so NASA funded the mission, and off we go to MU69. So let's have a little bit of more of an idea of what it is that we're going to go see in the Kuiper Belt. So this is an animation that was put together by Wes Fraser, who's a researcher at the Hertzberg Institute in Victoria. And what we have here is every object that we know of in the Kuiper Belt is shown in this little picture, and they're given different colors. So things that are kind of this purplish color that are here and here, these are things that have orbits that are a lot like Pluto's orbit. They're moving around the sun twice around every time Neptune goes around 3 times. They're stuck in this 3-to-2 resonance with Pluto. Then there's a set of objects that are this kind of cyan, pale bluish color, and those things are on orbits that have large inclinations and eccentricities that carry them far from the sun. And you can see on the picture there's lots of curly cues going around here, which are really indicating the orbits of these objects as they go around the sun. And then finally we have these red things, which are on these low inclination orbits towards they're right on the plane of the Kuiper Belt, and that's where we really thought, well, that's where we knew we had to search to find an object for the spacecraft to get to. So this is where all those objects are when the spacecraft leaves the Earth. And here's this little line indicates the trajectory the spacecraft's going to take as it flies out to get our solar system. We have here Pluto marked with a little circle and MU69. We didn't know where it was when we launched the spacecraft, but that's where it was found eventually. There's some structures in this plot that you can see. One is that you notice there are not really a lot of objects in this part of the sky. That's because that's the part of the sky where the spacecraft was going. That's where Pluto is, and that happens to align exactly with the galactic plane in Sagittarius. And basically, it just blocks completely all the light. It blocks completely our view of the foreground. There's so many background stars, they just saturate and block everything, and we can't see what's going on. I'm going to run this little video so we can kind of see the structure in a kind of a evolving way. And so here comes the spacecraft, and it's going to go past Pluto, whoosh, for the encounter, and then whoosh past MU69 for the subsequent encounter. And now let's tip the solar system over, and let's just see that is that plane of material, those cold classical Kuiper Belt objects that are in that kernel-y zone that we had to get to. And this zone here is completely empty because of the galactic plane confusion. If we did that survey now, actually Pluto's moved out of the galactic plane. This would be way easier to do. You can see here's Pluto now. It's way below the plane of the solar system on its very inclined and eccentric orbit as it goes around the sun. So Pluto's orbit is very different from this MU69 thing. We think this kernel of material is actually a leftover remnant from the formation of our planetary system. So that's why we wanted to see an object like this. It was really going to tell us about the processes of planet formation themselves. So, okay, so what are the things that we had to contend with? So this flyby is extraordinarily challenging compared to the passage past Pluto. The target is 80 times smaller in diameter than Pluto, right? So you're going from this giant object, Pluto, down to this tiny thing we're going to fly past. But we're going to get 4 times closer. So even though it's tiny and we don't really know exactly where it is in the camera field of view, we're going to get even closer, which is going to make finding it even harder to get it to the right spot in the camera field of view. We don't know where it is because we only just found it. We found this object in 2014. It has a 293-year period. So we have about 3 years of arc, so about 1% of the orbit that we've seen. And from that 1%, we need to pinpoint its location to within about a few tens of meters to a kilometer would be good. So extraordinarily high precision, a thing that's billions of kilometers away. You want to figure out where it is to within 1 kilometer. It's moving around the sun. You have to do all this in a very short period of time. The other thing was that we didn't really know what the environment around Pluto was, around MU69 was going to be like. So we had to plan a lot of contingency into the entire mission. And that contingency meant that, you know, looking back, we could have planned a completely different way of doing this project, but we didn't know really what we were going to be flying past and what it was going to be like. So we had to plan a very conservative kind of approach to this. The other thing is it's very dark, so we're not going to get a lot of signal off this thing until we're really close to it. We don't have a lot of power on board. The plutonium has been decaying away, and so we've reduced a fair amount of the spacecraft power. And we can't really do real-time adjustments. It takes about 12 hours for a signal to come from the spacecraft back to the Earth and back to the spacecraft again. And so if you want to have, say, in there, maybe you want to have a few minutes to make a decision, right? You're probably looking at 15 to 20 hours to really be able to make a choice about what the spacecraft's doing. So really, a day before you get closest, that's when you have to make your final decisions about what it is you're doing. So, okay, this is really challenging. So on January 1st, we had our closest approach. This is the kind of orientation that things had. So there's the plane of the solar system, this big green kind of area. MU69 is represented by this little circular ball. The white thing represents its orbit as it's going around the sun, and we can see the shadow that it is being cast by the object. And so the sun illuminated side is coming over from this side, and we have the spacecraft flying past slightly above where the target is. Okay, so that kind of, just to kind of get your idea of the whole orientation of this three-dimensional flyby problem. Okay. Just as we're getting up to Ultima Thule, up to MU69, here we have the Deep Space Network is tracking exactly where the spacecraft is. We use the Hubble Space Telescope and the Canada, France, Hawaii telescope data to figure out where the target was. We could do a downlink around December the 18th. We could downlink where the spacecraft is and where the Ultima Thule was in the spacecraft imager, and we can make some small course corrections. And then on December 30th, we downloaded the image of here's where MU69 is in the field of view. Try to adjust the spacecraft pointing to just basically point it in the right spot. So we couldn't speed up or slow down. That's not going to help us anymore. That's why on December 18th, we corrected the course a little bit. But on December 30th, we could turn where the camera was pointing ever so slightly. The thing is that even with all that, it's really hard to know where in space it is. I can tell this way, you can tell easily what's going on, but this way, it's really hard to know how far away from the camera my finger is without something to reference it to. So that's the problem we were having with MU69. We couldn't really tell its distance. We could tell its offset, but not its distance very accurately. So we had to make a plan for the flyby. Okay, so now here's the navigational images as we're coming in. You can see this star field is just like totally crazy saturated with stars. We do a bit of image processing and we get this. And then finally we get to this thing, which is the, get rid of that, which is the, what a subtracted star field is here. And maybe you can see in this image taken on August 16th, 2018, you can maybe just make out there is a faint smudge, and that's our very first observation from the spacecraft of MU69. It got brighter as we got closer, and we were able to switch over to optical navigation sometime in October, November period, where it became bright enough to be seen. So, but this is the raw data we're working with. The camera's got a lot of pixels that you see. It takes a fair bit of processing and massaging to get something that looks nice. Okay, what we're going to do when we get there, we're going to map the geology and the morphology of MU69. We're going to try to measure its surface color and composition and look for ices and that kind of thing. So we're just trying to do some science once we get there. Here's how the trajectory of the encounter looks like. And I'm emphasizing this to show you that right here in the center of this thing, we have the best black and white images being taken. Here's Ultima Thule. Ultima Thule is only 10 kilometers across. This is 20,000, sorry, it's only a, this is all done in miles here, so it's only a few, what is it? It's 20 miles across. And so it's just a little tiny tick here, and this is a 20,000 mile tick mark between here and here. So really, we're not sure where the object is to within this sort of large range here of this purple thing as we're flying up to it. And we have here 20,000 miles, 40,000 miles out is when we're starting to take our first images that are really high quality. Look over here, these tick marks are 15 minutes of spacecraft time. So the spacecraft goes from here to here in 15 minutes. So here's a tick mark and here's a tick mark. So the entire close approach sequence right here is packed into this one 15-minute window. So all of the really high quality close approach imaging is going to all happen tuned into this exactly precisely measured 15-minute window. But we're only going to measure, we're basically pointing the camera and flying along like this and hoping that as we fly along, MU69 will appear in one of the images that we take in this long strip. So, okay, that's what it looks like as we're just a few days out, coming in on December 30th. That is the last image we had before we had to make a decision of, is the object in the right part of the field? This was the data that came down from the spacecraft, and after doing some image sharpening, which is actually kind of image smoothing, this is what we thought it would look like. So I'm showing you this to give you an idea of the level to which you can kind of trust the image processing that happens to make the images go from these pixelated things into something that's smooth and easier for you to interpret intellectually. Right, you can sort of see that it's a bit fainter up here, it's a bit darker down here, so it's a small thing and a big thing, and you start to see some shape here. So, okay. And that's at around 1.9 million kilometers out is where we're seeing that. Each of these pixels is about 9 kilometers in size. So, okay, at the actual moment of encounter, this is the Deep Space Network. It's kind of fun to notice this. It's actually a video. These are the antennas all over the world pointing up towards MU69, and towards New Horizons. So in Canberra, Australia, 1, 2, 3 of the antennas are communicating with MU69. Over at Goldstone, one of the antennas is communicating with New Horizons, and this one is also communicating with New Horizons. So we really took over the Deep Space Network for the moment of encounter so we could make sure we got the kind of science data that we needed and make the observations we wanted to make. Okay, that is the moment of encounter. That was our very first glimpse at this target in the control room at the Applied Physics Laboratory at Johns Hopkins University in Laurel, Maryland. The whole science team is gathered there together to all experience this first look simultaneously. And the fellow sitting at the computer basically was responsible for bringing up that image as well as he could, and then as quickly as he could, and then everyone jumped over to have a look at it at that one moment. Someone said to me, oh, that looks like you guys must have staged this photo or something. It's like, no, this is just actually how it happened when it happened. There was someone there taking pictures of things and trying to capture the moments of things as they happened. So there's a real moment of discovery. I think you can see on a lot of people's faces, in their eyes and in their expressions, there's just this wowness to the actual experience of noticing that it's two round things stuck together. Wow, it's really weird. It is one of these sort of two contact things stuck together. What an amazing thing. This is what that image looked like. So it's about 30 kilometers from one end to the other. You can see it's kind of lumpy going around. It's got a lumpy surface. There's something here and it's a bit bumpy. But there's a lot of modeling in this image, which is basically noise. So that was a day after that other image where we could just see kind of a fuzzy bunch of pixels. And here it is at the closest approach. So this is the highest resolution color image, only it's been put together in black and white because the color is not that interesting. It's just a red object. And we have these two components. This is Ultima and this is Thule. And you can start to notice something odd in the shadowing here, that this is not a spherical body like it sort of stood out at the start. It kind of looks like maybe a squashed, I said it looked like an apple fritter, and this looked like a Timbit stuck to the top of it. I guess that's my Canadian perspective. There's some giant craters up here on the top or some kind of deformation. And we're starting to notice that the whole surface is not really covered with much in the way of small crater impacts. Here it is zoomed in quite a bit. This is the absolute highest resolution, best image that we got from LORRI. That is the high resolution imager. There's about 33 meters per pixel in this image. So this is extraordinarily high resolution. What we can see here is that there is this giant impact basin. There's this unusual feature here, which is kind of a ring, which looks like maybe there was an impact here and there's an old crater that's filled in. And we can start to see little bumps here and here. There's a few basins here or a few impact craters. There's some craters that are here that are more visible than elsewhere on the surface because of the illumination. The sun's coming in from down below in this particular orientation. So up here at the top, we have the best shadowing. And you can make out from the shadowing that there really are some craters on there. But there's no craters visible here. And it's very confusing to the science team as to why there are no craters. In fact, there are craters that are up to about 1 kilometer in size and then really nothing bigger than 1 kilometer. And it's a perplexing problem. Where are the impactors that should have been there to make those 1 kilometer craters? We think it's telling us that there are no 1 kilometer objects. There are no small objects in the Kuiper Belt to make these craters. A 1 kilometer crater would be made by a 100-meter sized impactor. And so it's really the lack of things bigger than about 100 meter in size in the Kuiper Belt that's causing this lack of impact craters. Okay, so we went through and we counted them all. Just a week or two before the actual first high resolution images came down, some of us on the science team, led by a former graduate student from the University of British Columbia, Sarah Greenstreet, we published a paper together where we predicted we would see somewhere on the order of 45 craters on the surface of MU69 if our ideas about the lack of small bodies in the outer solar system was correct, and it indicated that planet formation did not happen the way most people think it happened. It happened in a very different way, which involves some large-scale instability. And so I've numbered here everything that looks maybe like a crater, and you can see that there are around 45 things on the surface. So this is very consistent with our expectation of how many basins, or how many impact things we would see. There are basically the right number of features from that prediction that we made prior to seeing these images, I'll point out. So, okay, I know I'll skip over this. This is sort of more of a sciencey view of things here, but it really is just to show you that really at 1 kilometer in diameter up to here, this Maryland is the name that we gave the large feature at the top of Thule. There's this order of magnitude range where there are 0 impact craters to count. And I don't think Maryland's actually an impact event. I think Maryland's probably a formation event. And so really there are no impactors larger than something that would cause a 1 kilometer crater. So real mystery to what's going on there. Okay, so interesting thing to see. Oh, this little video doesn't run, so that's fine. This is Ultima Thule, and it has about a 16-hour rotation period. And that's good because it kind of gave us a little bit of a view of the rest of the object. And if I skip ahead here to, here we go, yep. So here we are. You can see this DRotated view. So we've taken all the data on this side here and put it all together at the same scale. And then over here, we're running it so you can see what it looked like from the spacecraft view. But when we look at this DRotated view, you can really see that there's this flattening to the structure that is Ultima Thule. It is not 2 round things stuck together, but 2 kind of flattened things stuck together, which is really peculiar and very unexpected. Here's some more of those kinds of views where you can see the strange squareness and flatness to this object. So let's go to this here. This is now a computer model of what we think the surface looks like. This is an early model that was made right after the flyby. We've adjusted this model so that it's not quite as thin anymore. It's a little puffier than this model shows, maybe a factor of 2 thicker across the main body. But it's essentially, this kind of shape, these 2 things stuck together in that way. And there's this. These are maybe some math overflow problems where this is probably not quite as pointy as it's being shown, but this gives you the general idea of what the shape. We're working on better shape models all the time. this is causing some real interesting issues. First of all, the surface is very flat. So how does it get to be so flat? We don't know. And the craters, we know we should be able to count craters really well on a flat surface. And so the lack of craters really is a lack of craters and not an inability to measure them. Here's an interesting thing from a high school physics kind of point of view, and actually from the geologists. It's very interesting. We map here, if you put a ball on the surface, where would the ball roll? So the black arrow is pointing the direction that the ball would roll if you put it down on the surface. So here, if you put a thing right here on this flat surface, it would kind of roll. It's a bit dipped in basically, and it would roll right to that center of that surface. You put a ball here, it would roll down here into this crevasse. But interestingly, if you put a ball on the outside edge here, it actually would roll into the middle. So it may be that when impacts happen, they create a bit of debris, and that debris rolls into the middle and creates this kind of smooth plane that would cover over some craters. That's a possibility. There's some interesting things here. If you put a ball here, it actually would roll up onto the side and then down into this little pit. We had a lot of fun animating this and trying to understand basically what way is up on the surface of this object. So, but you can see the gravity vectors are quite confusing. The other thing that we have is spectroscopy. So we have the spectra of the surface. This is what the spectra looks like in its sort of uncleaned up form. It's very ratty. You can see these broad absorption features. So this is around 0.5 to 2.5 microns. So this is basically infrared light over on this side. And we look at this infrared light, we don't see a flat spectrum. We see some very prominent absorption features. And those absorption features are consistent with things that we see on this object called Pholos, which is a centaur that we can see much closer, but not quite exactly like Pholos, right? It's not quite the same as Pholos. It's a bit different. We're still trying to understand what are the ices that are on the surface here that would give us this kind of spectral signature. Are these ices water? Are they methanol? What are they really? I'm going to show you one more slide here of the spectrum, which is this one, which is kind of zoomed in on that infrared part of the spectrum. And here we have these red dots, which are the spectrum we have from Cthulhu Regio on Pluto. That is that red patch right beside the big nitrogen glacier that I showed you on Pluto. And you can see that, wow, the spectrum of this object looks a lot like that red patch on Pluto, except maybe in this region here, where there's not as much absorption, maybe, and then over here where there's more absorption than is shown on Pluto. The blue spectrum is from Nix, one of the small satellites. And so you can see that Nix is not a good match to this thing. It goes all over the place, except maybe in this tiny little region here. We're really trying to understand what are the chemicals that are causing this and how do those chemicals connect back to understanding what Mu-69 is. But what we see, what we really have is we have this flattened object with an unusual gravity field that's very lightly cratered, and it's two things that have kind of come together. This seems to indicate to us that the way planets form is by some instability caused by gas in the disk and maybe some dust collapsing very rapidly to form this object. And the collapse, instead of taking 1 million years to form a planetesimal like Mu-69, this will take 100 years to form such an object. And so it's an incredibly fast way of forming planets, and it can happen in a very low density environment, which is what we see in this coronal region. There really aren't a lot of objects, even though it's the densest part of the Kuiper Belt, there is not a lot of material. And so really it's the only way you could form planets in that region. And it seems that that's what's happened. And that kind of planet formation scenario tends to produce two objects that will come together as a contact pair or will be orbiting around each other. And we're trying to see, do they produce these flattened structures or not? Is that important? And how do these ices connect into that story? It's sort of TBD. Overall, Ultima Thule is very red, and it's not like it changes from red. So here we have a kind of a contrasting image that shows where the red stuff is and where the less red stuff is, the stuff that's colored blue. But that blue stuff on the surface of Ultima Thule, right here, this region here, the neck region, connecting the two parts has a kind of a blueness. Maybe there's some more stuff up here. At the edges, we're not really, I'm not sure this is really red or not. But at these blue parts, the bluest that Ultima Thule gets is over here. So this is basically, this histogram on this side shows you how blue something is. And so over here is very blue, and over here is very red. And we can see that the bluest part of Ultima Thule is basically in the very red end of things. It is as red as the reddest things in our solar system. They're covered in these red material that is basically produced when cosmic rays or charged particles or something impacts the surface of these objects, breaks apart the ice, and creates this reddish, grainy material. That is what we see. And now we're trying to figure out what is it that causes this red material to form. So that is the next thing to try to understand in the cosmogenesis of this object. So there it is. Oh yeah, this is okay. This is not going to work. This is actually a stereo view that flip-flops back and forth, but only if I play this as a presentation, and I don't want to risk that because I think I might lose you guys, so I won't do that. But I do have this nice little video to kind of emphasize how hard it was to make this observation. This is the observing, these are all the frames basically that were taken during the close approach sequence. We're just going to watch all those frames go by. There they go. And so that was how we saw Ultima Thule. It basically, we were just taking images as the spacecraft flew along, and finally in a group at the middle, right here, it passed through the field of view of the camera, and then it went through. So we've taken all that data and we've registered it back together to create the image that I showed you earlier, which is that high resolution image at closest approach. We'll just watch Ultima Thule just go through the view one more time. By Ultima Thule, or by MU69. And here it is. After we went past, we turned back and we looked at the object as we were flying away from it. And so here it is passing through the field of the camera as we turned and passed by in the other direction. And that's the backside. And that is the two close approach sets of data. I'm going to just pause it there. You can see that the stars are kind of point-like, but Ultima Thule itself is moving so fast that we're actually seeing some blur in the images as it goes across our field of view. So we're really losing Ultima Thule very quickly. I just want to show you one more picture here. So here we are. We've had our encounter with Ultima Thule. We've passed through Pluto, and there we are. At the time this slide was made, which let me see, was on, no, we don't say, oh yeah, on the 12th of February. Yeah, 12th of February this was made. Already at that time, we were 32.5 million miles past Ultima Thule. It is a fast-moving spacecraft. We can no longer detect MU69 in the camera field of view. It's very small. We can still barely make out Pluto. So spacecraft's going at around 14.5 kilometers per second. So now what we're going to do, what are we going to do next? We're trying to decide if we can actually look for another thing to fly past. We think the spacecraft will run out of power sometime in the mid-2030s and somewhere around 100 astronomical units from the sun. We're just trying to work out, and we'll think we'll have some answers to the questions this October about really what will happen with the spacecraft next. So thank you very much for coming today. That was really fun to share with you the experience and the results from the New Horizons encounter.
Thanks everyone again for, I know you're there in the background, but if you have questions now, that would be a good time. So as people are typing, I do have a quick question for you. I was kind of surprised to see the poster from, as you were advertising the new, like the extended mission. When did you know it was 2 pieces? Because you had it on the poster. Did you know back then, or was that just a guess?
So the poster image was made up by one of my graduate students, Alex Parker, who studied binary Kuiper Belt objects as his thesis. And Alex was convinced that pretty much everything in that part of the Kuiper Belt was going to be binary. So when he drew up that image, he said, you know what? Everything's going to be binary, so I'm making this thing a binary for this image. And he was right. Pretty much everything that size and bigger in the Kuiper Belt, all those things they seem to form as binary objects. It's basically what they do. It's remarkable to me looking back at that image, and I'm going to just flip to it so people can be reminded of what you're talking about, because I'm familiar with it. Let's see here. I think it's about here in the slides. Oh, where do we go? There we are. So right? So here's that image of this binary object. Alex got so much of this correct, right? Even the ratio of the sizes looks about right. The flattening looks about, it's weird. I'm like, how did you get this so correct? And he just had developed such an intuition for these objects that's what he drew. So.
Fascinating. I don't know if you're still sharing your screen, so I'll read the question for you. Well, Barbara says, thanks, that was fascinating. And then John asks, you mentioned that the New Horizons craft was powered with plutonium, but later said that it was decaying away, so that would argue against it being very long-lived. So which plutonium isotope of plutonium is used? Sorry, I was trying to understand that. So basically he's asking isotope.
Right. Yeah, so I'd have to go back and look at the notes about which isotope of plutonium it is, but it has a short half-life, plutonium. It's not a long-lived isotope of plutonium. We're trying to use a small amount of material to generate a lot of heat. And so you do that by having a short-lived isotope. And so we have a short-lived isotope that is decaying quickly, and we're down to about half as much heat being produced now, even less. We're down probably to about 30% as much power coming off that plutonium as was coming off it at launch. So it's not a lot of plutonium, and it was a big controversy to get that plutonium onto the spacecraft and get it launched, because people were worried that if the spacecraft exploded, we would have a bunch of plutonium. So that's why having also a short-lived isotope is important, because if it explodes over the Earth's atmosphere, 30 years later, most of it's gone. And you don't have to, I mean, most of it is dispersed over the large area, so it's not really a risk anyway. And it's decayed so rapidly that it's not really a problem.
Thanks for the question. And again, if you do have questions, feel free to type them right now in the chat. I was curious, as people are thinking about the questions, I do have a few more. At first you were talking about us and them, and then you said, like, you kind of, when did you join the New Horizons team exactly? Because from what I understand, you provided some data early on, and then I think you joined the team really for the flyby. Is that really what happened? I'm kind of curious to the Canadian contribution to this.
Sure. Yeah. Thank you, Julie. That's so. Yeah. So there was originally no Canadians participating in this mission, and in fact, very few foreign participants at all. It's very much a NASA mission to get to Pluto. What was happening was, because they were struggling to find a target to go to, they really turned to the international community and said, can anybody? They would go to science meetings and give presentations and say, can anybody help us figure this out? And I went back after one of these meetings and I thought about the problem and tried to figure out, how could we help? What could we do to get this to happen? And so made this prediction of where the CFEPS team, and basically I, thought they should be. Where should they be looking? And worked with them to kind of hone that down. So that I was working basically as an external person, just kind of like, calling them up and saying, I got an idea here, let's try this. When the target was found, exactly where I keep saying we, but anyway, where I said it would be, the PI, Alan Stern, called me and he said, that's an enormous contribution to making this happen. We'd like you to become a co-I of the extended mission, just, because you made that contribution. So you don't really have a role. We're not going to give you work to do, so there's not really going to hurt you. Because often a co-I say, okay, and here's your chunk of work you've got to do. And I do actually do some work on the analysis, but really it was just, here you can be a co-I now because of their contribution of making it possible for us to have this extended mission. So I was it's a fantastic team to work with. It's a great honor to have had the chance to join and work with the New Horizons team.
Awesome. We do have other questions. So John asked, regarding the kernel ring, why don't the bodies concentrated there amalgamate into a planetoid, or do gravitational forces prevent that?
Right. So this comes back to the question of, how dense is this dense ring of material? And so those objects in that ring of material never hit each other. Although it's the densest part of the Kuiper Belt, you're never going to, that's where the most of the material is concentrated spatially. In a billion years, basically nobody hits anybody. And so in order to accumulate, right, into a bigger object and coagulate and form bigger things, you would have to have collisions. And you don't. They just don't happen. And so that's just the way it is. That's the material that's left. And the mystery basically is, how did we get to things that are hundreds of kilometers in size without having a range of material where it's all a kind of a collisional ensemble of things? There's no part in the Kuiper Belt really where you can say, aha, that is where the collisional processing was happening. There's a tiny range somewhere around 50 to 10 kilometers in size where maybe it was a collisional equilibrium distribution. But it's actually not quite collisional even in that small range. So the lack of material in the outer solar system, those very low densities, mean no collisions, no encounters. Things just stay the way they are, and a billion years later, they're still there.
Okay, so I'm kind of curious. I got to ask this quite quickly, then we'll go for the final two questions. So what's your take on the idea of a big planet maybe being out there very far away?
So that's one of the reasons that I show this image here, where you can see that there are no objects in this zone of the solar system. We can understand immediately why there are no objects there, because the galactic plane is there and it blocks our view to that part of the solar system. The evidence for another planet in the distant solar system, the thing that people call Planet 9, the evidence for that is based on the concept that the closest approach distances of these very distant objects, so the closest these most distant objects get, is actually driven by Planet 9's orbit. And that's the evidence that there is a Planet 9. But what I've come to the conclusion of, and the people that I'm working with on our solar system surveys, is that really what you're seeing is the effect of obscuration of parts of the solar disk because of the galactic plane and because of other observing effects. And that if instead you consider those observing effects, you discover that there's really not a preferential angle for any of these things to be on. There's not a preferential part of the sky where these closest approach distances come. So there's not really strong evidence then that from those angles that there is another planet out there. Interestingly though, there's a lot of weird orbits in the outer solar system. There's these high inclination things, there's things that have pericenters that are very distant from the sun. And we have no explanation for where those things come from. It's possible that there was other material in the outer solar system at some point that caused those orbits to be the way they are. It's possible that one of those objects is still there. So evidence of that, we've not seen it, and the lack of detection isn't a lack of existence. There's not really strong evidence from the angles that there's anything there. So I would say the evidence is pretty wishy-washy at this point for another planet, but it would explain a couple of intriguing parts of the problem.
Okay, interesting. So I'm sure that's, so we hear that in the news sometimes. I'm sure some students have questions about that. Maybe we'll finish the last two questions. We started a few minutes late, so we're going a few minutes over the hour.
I'm looking forward to hearing about the discovery.
Yeah, no doubt. Most amazing thing that I saw today is that Ultima Thule is two pieces moving together. Is there any other example of such a system? But I guess there is, right? Because you said Alex.
Yes.
Those.
Yeah, Alex said, that's what we're going to expect to see. And so I'm just going to, there we are. I have these backup slides. Where did it go? There it is. So here are some images of other things in the solar system that we've gotten close to and what they look like. And you can see, for instance, Comet 67P kind of looks a lot like Ultima Thule. Now, it's a lot smaller, but it's kind of like a shrunk down version, and maybe the surface has been ablated because it's a comet, and so a lot of stuff's come off of its surface. And then over here, I'm hiding it behind my video feed. So here we have Comet Hartley, which also is these two-lobed kind of things with a neck. And maybe Borelli up here is also two components. So this is kind of a common structure that you might expect to see in the outer solar system. We think comets actually come from the Kuiper Belt. And so the fact that we see all these bilobate things as comets means we really should have expected to see bilobate things in the Kuiper Belt. And so that's another thing that drove Alex's mind to think, okay, I'm going to draw this as two things, not one.
Interesting. I love that slide, actually. Okay, actually, just there are a few more questions, and JJ, if you have a few more minutes, we'll take them. I just want to take a moment. If some of you have to go, thanks for joining very much. We do have different webinars. I see a lot of new names actually on the list, so hopefully you're new. Not all presentations look like this. Like usually we do have it nicely set up in the sense that right now we see JJ's computer. But anyway, that was just a technical glitch today. The talk was amazing regardless, and we do have other presentations coming up. So check out our website if you want to come back. But JJ, if you do have a few.
And I'll take full responsibility, Julie, for the technical glitches because I.
It's okay. We made it work. And actually, the problem was that we wanted to show your amazing animations, and that's why we did this way, because you had so many nice videos and animations. Okay, so question here. Based on the size and shape of Ultima Thule, there must have been some collisions in the past, though. And I'm guessing that's referring to all the impacts that you think there. Oh, no, that the fact that there was not a lot of collisions in the Kuiper Belt.
How do you get two objects to come together to form like this bilobate thing if there aren't very many collisions? It's kind of a curiosity. And so what the modeling would indicate is that planets are forming, these planetesimals, I should say, are forming when there's a bunch of gas and dust, and the gas and dust is flowing around the sun, and a little bit of it accretes to become more concentrated, and the gravity causes an instability. It's kind of like smoke rings flowing up through the air. You just get a spot where there's a little bit more of a concentration and you get instability. One of those instabilities is called a streaming instability, but some kind of instability in this disk. And that aggregates the material together and it collapses big chunks of material, and the central object of that collapse would be something on the order of 100 kilometers in size. But a whole bunch of smaller things will also be produced during that collapse. And the local density in that collapsed environment is very high. So we think what's happened is that during that collapse, a whole bunch of small fragments are created and they spin off of MU69's, off the central collapsing point. And MU69 is one of those little pieces of debris, basically, that shot off during that collapse process. And that's kind of our best idea of how you get two things to come together, even though the density in the local environment today would say that's impossible. So it must be something about the formation location, a super high density of material. And one of the really important things to realize is that the color of one side and the other is exactly the same. Their spectra are indistinguishable from each other. So they basically, both pieces formed from the same piece of the solar system. One of these objects, one of these stuck together objects, compared to another one in some other part, are going to be a bit different. They're going to have slightly different shades of red. But when we see them together like this, they always have exactly the same color on both sides, which tells us they form locally in this aggregated way, and there is some difference from one aggregate forming over here and another aggregate thing forming over there. So I hope that kind of makes sense.
Learning a lot too, actually. This is fascinating. And thanks. And the last question that we have now is from Arthur, and he asks, when will we know about the next target?
Arthur, I hope we know soon. So in October, this subset of the New Horizons team is going to be meeting in Baltimore, I believe we decided, and we're going to make a decision about what to do, what we're going to do. We're going to spend the summer basically doing a lot of modeling and a lot of predictions and analysis and try to come up with our best understanding of what's possible. And then we're going to get together in Boulder and talk to each other about what we think is possible and make a decision about what to do. If we think that it's possible to find another target to fly to, that will become the primary thing that we will do. We will start an enormous campaign to try to find something else because we have a spacecraft in the outer solar system. That spacecraft is perfectly healthy and working, and let's use it for the optimal purpose that it has. But if we feel that the chances for another encounter are too low, that our chances of finding a target are too low, we'll probably start doing what we call distant Kuiper Belt observations, where instead of trying to fly up to something and look at it close up, we'll look around where the spacecraft is and we'll observe some of the Kuiper Belt objects that are in that neighborhood. There's probably about a dozen objects that we could kind of take long distance observations of. They would just be points of light, but they would provide us an interesting perspective on those objects. But stay tuned until basically November or so, when maybe there'll be an announcement of what we're doing.
This is fun. It's like you have this great working toy out there in the solar system. Like, what do we do next with it?
Absolutely. And they're enormous, you know, I mean, the team, everyone has their thing they want to do.
Yeah.
Yeah.
Awesome. So I think we'll end here. Actually, I think, okay, final question, if you can take it. What was the cost of the program? It just came in.
Okay. So the initial mission was $891 million US. So that is every penny counted, from the scientists working to design the mission for years, the engineers, the technical crews, the launch vehicle costs, the rocket, fuel, plutonium, all of it added together to get to Pluto and fly past Pluto and downlink the data and analyze the data and do the science. That was $891 million was spent on that. Almost exactly 10%, $83 million has been spent since then, or is allocated to be spent on exploring Ultima Thule. And that, again, pays for about 50 scientists' salaries, the downlink antennas, a couple of a large team of engineers to properly plan everything out. And so when we add it all together, we're talking about of order $1 billion is being spent on this particular space mission. So this is not, you need to be careful about what space missions you do. Getting to Pluto, Pluto was the last part of the solar system that we had not yet explored. Now we've explored it and we've learned a lot. And I hope our understanding that we've achieved is something that can be seen as valuable in exchange for the cost that it was. So, and so now, and I say $1 billion, and so I talked with a U.S. senator actually about the cost of this mission, and I was like, I mean, it seems very expensive to me, and he says it's 10 miles of interstate. Okay, we could spend $1 billion and explore Pluto, or we could build 10 miles of interstate. You tell me which one you'd rather do.
Yeah, that's an interesting comparison.
Yes.
Okay. Well, thanks a lot, JJ. That was so generous of you for sharing your knowledge and your passion for it and all the questions afterwards. Thanks a lot, everyone, for joining us for this webinar. I think, JJ, if you can stop your screen sharing, I think there are many comments coming up thanking you. So if you know how to come back.
Sure. How do I stop the screen sharing here?
Actually, hold on.
There
we go.
I stopped.
Perfect.
There we go.
Back with us.
Yeah.
So yeah, thanks a lot, everyone, for joining.
Yes.
And thanks, JJ, again. So as you're leaving, if you want to write a word for JJ.
Thanks very much, everybody.
Thanks for staying till the end. Actually, almost everyone stayed.
It was great to have. I was about to type a message back to everybody. I was just going to say it was really great to have everyone join the Adobe Connect here and discover the universe. Really appreciate that you took the time to learn about New Horizons and NU16.
Awesome. And I know, JJ, I'll check back with you, but I know you agreed that we could share some of your actually content, like the PowerPoint, so part of it anyway. So I think that's huge benefits for people who participated, because they'll be able to use some of that stuff in their classroom. So I'll check with you first before sharing everything, though.
Oh, yeah.
Okay. Well, thanks a lot, everyone.
Thanks.
See you next time.
Bye, everybody.